We've seen halogenation of a carbonyl, alpha halogenation of a carbonyl under acidic conditions, and now we're going to go into basic conditions. You have a different thing happen here. With an acid, under acid conditions, you only have one halogen adds and it stops. But with basic conditions, you have a different intermediate form. Instead of the enol, you have the enolate. So what happens is sodium hydroxide, under equilibrium conditions, deprotonates this alpha carbon. Then the enolate does attack on the chlorine, and you get chlorination of the alpha carbon. This now is a more acidic proton right here that is alpha to this carbonyl, because now the chlorine will help to stabilize a negative charge here. So this is preferentially deprotonated over any acetone that might be in there. So the sodium hydroxide deprotonates this, and then this does attack on the chlorine, and you get dichlorination, and then you get trichlorination, and then you can start doing all that all over on this side and getting chlorination on every single alpha hydrogen removed and replaced with chlorine or bromine. So the basic conditions are rather uncontrolled, but we can use this to our benefit. Look at this. If you have a methyl ketone, what can happen is you can do alpha halogenation having excess halogen in there, and you will tribrominate a methyl that's adjacent to the ketone. Now the hydroxide can attack the carbonyl. It's going to be attacking it occasionally anyhow, but now once this is tribrominated, hydroxyl attack of the carbonyl gives you this tetrahedral intermediate. And look over here, you could have hydroxylide eliminate, or you can have this tribromomethyl anion eliminate. That tribromomethyl anion is very stabilized by those three bromines, and so it's an excellent leaving group, and it leaves preferentially, and you end up getting the carboxylic acid. So this is a method of turning a methyl ketone to a carboxylic acid. We call that reaction the haloform reaction, because the byproduct of this reaction is a haloform. A methyl with three halogens attached is called a haloform. So what is the outcome of these reactions? Well, let's analyze this first one. We have no alpha hydrogen here, so nothing will happen on this carbon. But here we have a methyl group, so we can actually do the haloform reaction under these conditions. That will triiodinate this methyl group, and then it will leave as iodoform. So what will happen? We'll make benzoic acid an iodoform. If I look at this compound, I see that I've got two different alpha carbons, but there's no methyl group, so an iodoform or a bromoform reaction can't occur. You can't have a methyl. There's no methyl there to be brominated and then leave. So what happens? Well, under basic conditions, if you have enough bromine around, you're going to get complete bromination, complete bromine replacement of all of the alpha hydrogens. And so this compound would result. So how can you make this ketone right here, how can you make this acid right here from this ketone? Well, a carboxylic acid and a methyl ketone, we know that we can use a methyl ketone to give us a carboxylic acid, but there's a difference between this methyl ketone and this methyl ketone. How can I put alpha beta unsaturation in there? Well, I could do it from this bromine compound. How can I get this bromine compound? Well, I could do acid bromination. The enol would form preferentially on the more substituted side, because the ene would be more stabilized by greater substitution, and so the bromine would preferentially go here. You then treat with sodium hydroxide and it would give elimination, And then to take the methyl ketone to a carboxylic acid, we would use chlorine and sodium hydroxide, and it would end up giving us a carboxylic acid. Alpha halogenation only occurs with aldehydes and ketones. This can be either acid catalyzed or base catalyzed, and you know the difference between them now. Acid catalyzation gives you mono halogenation, and base catalyzation can give you pretty much unlimited halogenation. Acids do not form enols, and so they don't undergo this reaction. But if you really wanted to do it, what can you do? You can make the acid halide and then do a bromination. So let's look at an example of that. If I use phosphorus tribromide, I will end up making the acid bromide. And if there's bromine in there, I can then halogenate the enol that will form. Water then will take the acid bromide to a carboxylic acid. This right here, treatment with water, will take this then to the carboxylic acid. And the net effect is alpha bromination of a carboxylic acid. So the conditions would be phosphorus tribromide and bromine. Here's an example. Here is heptanoic acid. If I treat it with bromine and phosphorus tribromide, what do I get? I get bromination on the alpha carbon. The water here took the acid chloride intermediate and brought it back down to the carboxylic acid. So what is the outcome of all of these reactions? Well, let's look at the first one. This is a repeat of the previous reaction. So all that happens is that you get alpha bromination of the acid. That's because we have water hydrolyzing that acid bromide down to the carboxylic acid. But if I look at the other two, I don't have water, I have ethanol, and I have ammonia. Well, if I form the acid chloride and then I treat with ethanol, what will we get? We'll get an ester. And if I take that acid bromide and I treat it with ammonia, what do I get? I get the amide. So we actually can use that acid intermediate to go other places than just back to the carboxylic acid. Alpha halogenation can be used to induce conjugation on an ester or an acid derivative. So we used alpha bromination on a carboxylic acid and then treated the acid halide with ethanol. Now what can we do? We can treat this with a base, and it can be a mild base like this one, pyridine, and it will then induce elimination, and we get alpha beta unsaturation on this ester right here. Enolate ions not only can undergo halogenation, but they can be nucleophilic, and they can attack electrophiles. Now, there are hard and soft electrophiles, and the electrophile determines which end of this enolate would act. Hard electrophiles like acids will protonate the oxygen. Soft electrophiles like alkyl groups attack the carbon. And protonation on the oxygen, well, that's reversible and will give you the ketone. We're not really interested in that. But alkylation with an alkyl halide, though that modifies the carbon chain and is very useful in synthesis. So what we see with enolates is that they will do SN2 on an alkyl halide. Remember the limitations that we have on SN2. We'll go over those in just a minute. Along with alkylation, we will see that if you have an acid group beta to a carbonyl, you can do decarboxylation, and we'll see some examples of this. This is primarily associated with the malonic ester synthesis or the acetic ester synthesis, but it's not limited to that. anytime you have an acid group beta to a carbonyl, if you heat with acid, you can decarboxylate. So we'll look at this a little further. When we undergo alkylation of the enolate, we need to remember that it is an SN2 reaction. So primary, allylic or benzylic is best. Secondary is going to give you some problems because elimination is going to compete. And tertiary will not go. You're going to have elimination only occur. Look and see what happens in this alkylation. Here's the enolate, and it's doing SN2 on an alkyl halide. Notice the effect is that you're putting an alkyl group, alpha, to the carbonyl. Let's look at an example of that. So here is a cyclopentanone, and these are the alpha carbons. We treat with LDA. It gives 100% deprotonation and changes that ketone to an enolate. Then we treat with an alkyl halide, the primary alkyl halide, and we get SN2 on it. Notice the effect is cut off the bromide, take away a proton, and you attach the alkyl halide to the alpha carbon. So this is called alpha alkylation. Two additions can be made if you have two alpha carbons. Here's an example. Here is, this is called a lactone. We treat it with LDA and it makes the enolate. We do nucleophilic displacement on this primary alkyl halide and that gives us methyl alkylation on the alpha carbon. Treat it again. We make another enolate. Treat it with another alkyl halide. Notice we have both of them now attached, so you can do them in sequence like that. So you go ahead and determine what is the outcome of these two reactions. Okay, in the first one, we have treatment with lithium diisopropylamide. Where are we going to get deprotonation? Here or here? This is more acidic, so that's going to be deprotonated, and then we'll get alkylation of the methyl group right there. Where are we going to have, well, here we have treatment of this ketone with LDA, and by the way, aldehydes work fine too. LDA, here is the nucleophilic, the center at which nucleophilic substitution can occur. You can't have it, remember, on an sp2 carbon. So what happens? We get the enolate, and it does an SN2 on the primary carbon, and we end up getting this alkylated ketone. So you determine what is the outcome of this reaction. Well, notice this is a dicarbonyl, and a dicarbonyl is 100% deprotonated by sodium methoxide. So that's great. It's going to deprotonate this. Here's my alkyl halide, and what do I get? Substitution on the alpha carbon.